Okay, thank you to be here for the lecture of today. Today we will see together an interesting variation. I hope that I would like to show you two examples in which the nonlinearity, or better to say the model, but in particular the nonlinearity or nonlinearities are represented or, yeah, in the model, considering also the output. As I told you last time, I have an electronic version, I mean, presentation of all material. But you remember I told you there are some errors. Sometimes the error, which, I mean, not conceptually errors, but how possible to say the students very often, the student who realized this material was not able to interpret my calligraphy. This is in this sense. But anyway, I will upload nevertheless. If something is not clear, you can contact me anytime. But again, very important that you download the software. This week will be everything in my study because we are up to date. We are really in the examination time. This means give me in a couple of days. Tomorrow, for instance, I'm out of my office. But let me say between Wednesday and Thursday, we will have everything. And then I will communicate per email that the material is there. Okay, we can see here the word advanced. I don't know if you see correctly, because I see in a strange way. I don't understand how I can. I see as if in the contrary. For me, it's a little bit difficult to. But I hope that you see correctly. Did you did you see correctly? X1 derivative is correct. It's just in my computer. This is strange, but anyway, for me, it's okay. Look, we have a system of two states, nonlinear, because of this square here. And in particular, look, we have, it seems from the explanation, this parameter A is a parameter to be estimated. This means we have a physical nonlinearity, x squared, x2 squared, is something you remember, which I told you is physically an state x2, which represented the energy somehow. It's quite abstract. Why I'm using quite abstract system? Because here we are not we are not here just for engineers. And I would like to emphasize also more the concept that our methods, our approach is quite general. Believe me, you can apply in population dynamics, in biological dynamics, in everything which you want, in the sense, assuming that the system change over time, which we can, an economical system, in which we can consider some possible energies. Also, money, you remember I told you in the bank, uh, is energy. If I have time, I try to, at the end, to reconsider an easy example in economics in order to understand a little bit better what I intend. But anyway, believe me, it doesn't matter which kind of system I have. At the end, you have a dynamical system. This means two differential equations, or one differential equation, or 100 differential equations. A little bit complicated. It's not more complicated than two. Uh, Probably just a little bit boring, but of course, with 100 states, it could be that I need to measure more than one state, no, in order to obtain the observability. Do you remember the concept of observability? But anyway, structural or physical nonlinearity. And here, if really I want to estimate A, or I need, better to say, to estimate A, we have also another nonlinearity because I have to augment the system using, I show you now more concretely, I have to consider not the state, and the augmentation, in this case, because of the product, generates another nonlinearity. Now, the nonlinearity generated by A as a state, augmented state, which is not exactly, I don't want to say this is not, isn't a parameter, no? This means physically, probably, or in general, the parameters have meaning. But of course, if I augment, this means I try to model the parameter as an element which change over time, and then somehow we associate an energy, because the state reflects always the energy, which is not directly, let me say, related to the physical energy, but nevertheless is there. We can think about that because A change over time. Let me be more concrete. Look what I intend. If I call A equal x3, we can see instead of A, this is the same system, no? Or at least the first two equations are exactly the same, like here. The unique difference, instead of A, I have x3. I told you before that, yeah, x3 is a Gaussian variable inside the Kalman filter. Here isn't a constant. In this context here, let me see if I can find, yeah. In this context here, it seems to be x3 isn't a constant because the derivative of x3 equals 0. Makes sense because here inside, we are not in the Kalman filter, not yet. Because in the Kalman filter, you remember, I have to put hat, minus, hat, hat. It's not just a formal representation because deterministically, A is a parameter. A is a parameter. As a parameter, I would like to say directly that its derivative is equal to 0. But if I assuming that A change over time, A of t, like here x3 of t, I am assuming somehow that is something we change over time. This means it's not exactly in a constant. Using this language here, I am saying I give you an identity to x3. X3 is equal A. No? This is another notation in order to have all state in form of x, which change over time, but just inside the Kalman filter. Do you remember that the Kalman filter is basically an algorithm which, starting from a deterministic model, gives to this deterministic model an aleatoric character, a statistical character, using the matrix Q. I will come back again on this. Just to introduce the topic. Look now. With this lecture, I have the possibility to repeat also some concepts. I already told you about this form. If I discretize this model here, believe me, forward discretization. In this course, I told you just of forward discretization. I told you that we have also a backward discretization. I told you that we have Oin discretization, Runge-Kutta discretization. I don't have time to tell you, in particular in bachelor, it's really a little bit too difficult. But if you want, we can go a little bit more in depth together with projects. Sometimes it's useful to change the discretization, but believe me, changing the discretization, we have a different Kalman filter. It's of course isn't a variation of Kalman filter, but I don't have time to do with you. But in any case, keep in mind that the discretization also makes a difference between the Kalman filters. Here is forward, which is the most used, but not in particular case, not the best discretization. Depends on the system. Do you remember I told you in stiff systems in which we have at least two dynamics, one fast and one slow, of course, the way to approximate as the choice of TS could be a critical one. I don't have time to add something more about that. Jacob, yeah. Why this expression here? Just justify. This is easy, no? The last one. It's easy because the derivative of x3 of k with respect of x1 of k minus 1 is 0 because we don't have here the dependence with respect to x1 of k minus 1. Here the same, we don't have the dependence of this equation with respect to x2 of k minus 1. This means 0, 0. Why 1? Because here the derivative of x3 of k with respect to x3 of k minus 1 is 1. Because it's linear here with the coefficient 1. The derivative of x3 of k with respect to x3 of k minus 1 is 1. Let me check this one, the second line. Why ts? Because it's the derivative of x2 of k with respect to x2 of k minus 1. Excuse me, x1 of k minus 1. The derivative, to calculate this element here is the derivative of x2 of k with respect to x1 of k minus 1. Excuse me, it's easy to show you than to explain with words. We can see that we have just this element here. Let me see. Ts multiply 1. Why this one? This element here is the derivative again of x2 of k, this time with respect to x2 of k minus 1. Why 1? Because of this. Why 4 times tsx2 of k minus 1? Because the derivative of this element here with respect to x2 is 4 because of the 2 factorial, minus 4 to be more precise, of x2 of k minus 1 multiply ts. Anyway, you can check a little bit alone at home because we have seen many times. No? But very often when the system is more complicated, I use the symbolic tools of toolbox of MATLAB. Do you remember we have seen this sims, I think, this command sims. I will upload nevertheless everything we used just in another context, but it is able to calculate symbolically the derivative. If the system is complicated, of course, it makes sense to use. But anyway, we can do also by hands. Calculated in the correct states. Here, there isn't a comma because let me see. It's not visible, but we have also u of k minus 1. It's not visible, but because I don't have place, but the comma indicates this u of k minus 1. Excuse me, x3 of k minus 1, and I forgot to write u of k minus 1 because it could appear. In this case, don't appear. Excuse me, I make a little bit confused. Calculate x1 hat, x2 hat, x3 hat. Theoretically, I have to write comma u of k minus 1. Everything at u of k minus 1. This means at the previous corrected value, but u is nevertheless the input. It's not wrong because we can see that we don't have u. Because the nonlinearity does not involve u, but it could. Okay. Let me, before going ahead, reading this sentence here, and then I would like to improve a little bit this zoom, because for me it is not easy to work with this system. Look at this. I am free, very important, because in Kalman filter, when I was young, but also now, I was fascinated by Kalman filter because of this concept here. I am free, first of all, to apply the Kalman filter everywhere I have in the dynamical system. But to think strongly that equation 1, but not only equation 1, I show you a little bit later, even though I will consider just one case, can be considered as an output equation. Not only equation 1, also equation 2. Theoretically, also equation 3. Everything which I represent with my concept can be considered as an output equation. Very interesting aspect, because until now we have seen everything represented as a state, in state, exactly what I am doing now. can be represented, and this means, excuse me, this means that the system can be represented in the following way. Before commenting this, let me stop. Let me try to improve the format of Zoom, because for me it is difficult to orient the slide. Let me stop the presentation. Okay, we can see here that basically we have the same three equations as before, the same three equations as before, but please pay attention. The system, again, is represented formally with the same three equations, but it seems that, according to what I am writing here and what I will implement in the Kalman filter later with MATLAB, that the first two equations, or the first two equation, the sense, the equation, the dynamics x2, dynamics 3 represent the state equations, and this equation here is the output equation. Of course, please, at home, this could be also in a project. Why not? To compare this approach with the other one, in which I will consider x2, the dynamics of x2, or let me say this equation here, as the output equation, and x1 in the state. We can see that we have basically three possible combinations. Anyway, I will show you just one, but the other combination could be considered a possible project. Again, and this is important to discuss today at the end, the project must not be necessarily a concrete project. But of course, if it's concrete, this is better. But believe me, a concrete project which came from the reality very often is relatively difficult. This means in the complementary study, in the bachelor context, not necessarily is I required in a concrete project. This means the idea you have to verify, or that certify, better to say, that you learn the Kalman filter. At the end, nevertheless, I will show you quickly in a possible model in economic systems. Okay, look at this. The same three equations, but we will see that in the Kalman filter, they have a different meaning. Because here everything is represented in states. Here is the Jacobian in states. I don't know. In any case, I have the let me say the implementation of this, but anyway, this is, let me say, standard. Why standard? Because typically we try to represent, or at least for normal system, we try to represent everything in the state. What is the normal? Yeah, this is a little bit too difficult to explain. But in any case, believe me, sometimes to represent in a different form, also for standard, let me say, systems, we have advantages. We will see exactly also now, because look at the Jacobian, the state Jacobian. The state Jacobian consists of a matrix 2 times 2, because the state Jacobian should represent, do you remember, Jacobian reflects the Taylor approximation, of the state representation of the system. This means we have just two states, x2 and x3. And what is this element here? This element here is the derivative of x2 of k. This means of this expression here with respect to x1. You look, to respect to x1, there's an error here. No, excuse me, to respect to x2. Because x1 is not, please, sometimes I made a mistake too, because x1 is not a variable, how possible to say, is an output variable. This is a little bit the concept. This means the state variables is written here, state equation, state variable, x2 and x3. This means here I have to represent the Jacobian, the approximation of the state variable or the state equations using x2 and x3. This means this element here reflect that is the derivative of x2 of k with respect to x2 of k minus 1. This means 1, we can see 1, and 4 ts x2, we have already seen this, no? Multiply ts, yeah? I already told you, because it's the derivative of this, gymnasium. No? Y0, because we have to do the derivative of this with respect to x3. x3 is not present. Why 0 here? Because the derivative of this expression here, which is x3 of k with respect to x3 of k, with respect to x2 of k minus 1 is 0, because we don't have this. It's 1 because, of course, the derivative of x2 of x3 of k with respect, which is this one, with respect to x3 of k minus 1 is clearly 1. We can see already from this equation here, excuse me, from this Jacobian here, we reflected these two, the derivative of these two equations here. Do you remember the Taylor approximation? Quite easier than this, easier. The dimension, easier, not wrong, but the dimension of the normal representation, with respect to this representation here for the state, just for the state, we have a matrix 2 times 2. Here we have a matrix 3 times 3. This means here we have 9 elements. And here we have just 4. Of course, we have now to consider the Jacobian, the output. Do you remember when I introduced this general nonlinear Kalman filter or extended, we have 2 Jacobians. At this moment, we have seen just 1 Jacobian because we have seen the nonlinearity in the states. But of course, it could be an advantage because smaller, let me say, matrices means, remember this concept here, to improve, to increase the level of observability for different reasons, as I told you last time, for different reasons. Because the dimension of the system to be estimated plays a clear role in the, let me say, in the level of the information which I have to manage. Because less channel means high density of information. Do you remember last time I was a little bit more precise? Look at this. Output Jacobian. Of course, we have to consider that this approximation, or that this Jacobian will reflect the Taylor approximation, is not enough in the Kalman filter, because the nonlinearity, or in general, we have another equation, but in particular, if the system is nonlinear. If the system is linear, it's clear that it's a little bit more easy, but in any case, this is my output equation. Very important, the concept of output equation we are introducing today, because you remember y is equal h not capitalized of x. I don't know if you remember this. I will come back with the lecture now a little bit later. Y equals h of x is not only a map of what I am measuring, could be also a part of the model. An h could be also a nonlinear system. But very important, this fascinated me, fascinates also now. I can choose as I want. This means it could be, this could be an interesting project. It could be that this guy, we will see also at the end in economics, it could be that it's more suitable to choose another version of the representation instead of this one. Very often it's a little bit difficult to choose, but look now, which one is the best. But of course, we can let me say, test all possible combinations. We have 3 possible combinations, and the standard one, let me say the standard one, for Kalman filter, and then to compare using a norm, for instance, the a posteriori error covariance matrix, or the trace of this matrix, or one element of this diagonal matrix. The trace is, do you remember, the sum of the diagonal element of a matrix. Why a posteriori covariant matrix? Because it's the diagonals, the diagonal or the diagonal elements are the variance of the corrected estimation. Why this here? This element here is the x of k with respect to the x k minus 1. Why that? Because the states in our representation, you remember, this is a very important concept. The state in our representation, x2 and x3. x1 is an output variable in our choice. This is very important. It's free. How to represent the system is free. The derivative. Why this one? x1 okay with respect to x2 okay minus 1. This means I have to consider just this element here. With respect to x2 of k minus 1, I have just this element here, which multiply ts. Is it that? What about this? Is again the derivative of x1 of k, the output. No? Do you remember in the lecture, if you look again, the lecture is day h with respect to x, but states, the state is x2, x3. K minus 1 in accordance with the definition. No? This equation here, with respect to x3, I have to consider again this. Now the derivative is t2 multiply x2 of k minus 1, because the derivative, you remember, Ginnasio, this will cancel. Again, as before, no surprise, u is not present because the nonlinearities don't involve u. Look, basically we have here, if you look at these two Jacobian, you remember H capitalized is the Jacobian of H not capitalized field. It's not a field equation or expression. In linear case, let me say, if I have just a variable, in linear case, it's not correct to say, because if the equation is complex, but also linear, nevertheless, we have a complex matrix. But if the output includes just the map of the sensor, do you remember we have 1, 0, 0, 1? But of course, it's not enough to say in linear case, because if you don't have here the nonlinearity, in the sense you have a plus, and nevertheless have a more complex system. But in general, look, you have 4 elements here and 2 elements here. Just with this rough consideration, we can see 6 elements with respect to 9 elements. Also, this rough criterion is important to evaluate how complex is the algorithm, because at the end, of course, the number of states are important, the structure of the matrix, Look, here we have 1, 2, 3, 4, 5, 6 element, not 0. 6 element, not 0. It is not quite sparse matrix. 6 element, not 0. This means 6 divided 9. Here, half of the element is not 0. This means the structure of the system is something easier here. But also the number of elements, not 0. The number of elements, 1, 2, 3, 4, in this representation. And here we have a 6, no? Yeah, twice. The number of elements indicates also the number of calculations. Don't forget that practically these algorithms must be implemented inside the TS. But in general, we don't have to really be more advanced to understand that less calculations easy to implement, in the sense I don't have to have a microcontroller really extremely fast. No? This is a little bit just roughly speaking. It's clear, if I were to just to calculate 1 plus 1, it's easy in the sense it's quick. Instead of to calculate 1 plus 1 divided something plus, just allow me to be a little bit trivial. Very interesting question, nevertheless. Is the diagonal structure a drawback for the convergence of an extended Kalman filter? We have here. Do you remember this question was as a question which I, or a problem or indication, remark, which I proposed when I analyzed the observability. Because remember, I told you, if you don't have connections in the system, this risk to be, how possible to say, unobservable. But this sentence, I don't want now to comment this because a little bit for more advanced courses, but this is valid, the sentence here, is valid for the whole system, excuse me. And in particular, from the original system, because you remember this important concept which I told you at the beginning. Independently of the representation, independent of the representation. You remember this? I insisted when I told you about the cascaded Kalman filter, when we estimated with two connected Kalman filter as an example, resistance, inductance, or two parameters with two separated Kalman filter, but connected nevertheless, separated in the sense of Jacobian, but connected in between the rest of last time. I told you the observability does not change. Could change its formal representation, but if the system is observable, remain observable. If the system is not observable, we cannot gain the observability. I don't want to go in depth on this mathematical explanation. We can discuss together. This means apparently it seems to be not observable, but the system remains observable because these three equations, believe me, I didn't check here the observability. This could be also a part of the possible project. The system is observable. This means it doesn't matter how I can represent it. And moreover, the connection is not related to the Jacobian, but is related to the system. Of course, is the system yeah, I would like to conclude this with this sentence here. We can discuss together about this, but at this moment in this course in the bachelor, this means basically exactly what I tell you, because the system is in the states, it seems to be not connected. This is valid, but it's connected through the output. I mean, the system itself physically is connected, is interacting. This is the concept of the observability, because I get information, at least we have a possibility measuring something, in which we have a measurement is clear, is important. We have seen at the beginning of the course to get information. This means the system is observable. Let me conclude, and then we will implement. The idea is today to implement this, to repeat a little bit this aspect here, and I would like to leave you some task for the possible implementation or project, not necessarily of the system. Here we will see also an economical system, but before economical system, I show you at least theoretically, I will send you the software nevertheless in another example. But this I will implement also, I will show you the implementation. I will upload also the last example, even though I don't show you the equation in MATLAB. But let me show you this. I would like to do some considerations. Let me see if I can improve. Yeah, here again, I forgot to say, I don't want to go in depth on this because do you remember this implies a question and a topic which yeah, I didn't tell you. Do you remember in the slide, in the MATLAB, I always considered K, the Kalman gain, in output, even though I don't need directly for the next step. Do you remember? I told you many times. But very often it is important to debug. I mean, we have also variation of Kalman filter which we can use. But in general, for the basic Kalman filter, for the basic, we are in advanced form also. Kalman gain is important to analyze what happens. We can see here how sensitive is the Kalman filter. Let me say, I can translate this concept here in Kalman filter. This P up to -1, P up to minus, no, the a priori error covariance matrix. Multiply this is somehow the kernel of the Kalman filter because P minus plays an important role in K and so on. Therefore, how sensitive is this element here, the Kalman filter, to update KK? But I didn't tell you about that. Therefore, I don't want to tell you here. Now, let me consider another variation. Yeah. Again, with these two Jacobian, I can implement. Remember, Kalman filter, the project for you is easy because you can download. You should download just one file which can help you in your topics and to modify it. The unique thing to calculate is the model, to organize the model in this form, standard form, choosing a different variation to calculate the Jacobian or the Jacobians, and then to change the structure which you can find in my study. The Kalman filter wants, or at least each basic form of Kalman filter, extended form of Kalman filter or unscented form of Kalman filter, which I didn't tell you in this course, they have a basic structure, and then we will change in accordance to our goal. Look, the output Jacobian is this one. Look now, and then I will show you with the simulation what I can do nevertheless. Again, this is the output. And let me consider now x1 of k circa is 1 of k minus 1. Why this hypothesis of this assumption? When we consider an assumption, we have always discussed an assumption. You remember when I told you the assumption of when I approximated the system, the dynamical system, or let me say nonlinearity using the Taylor approximation. You know, Taylor from Gymnasium, but anyway, we have to discuss how conservative, no? What I am losing, what I am gaining, with this, what is the advantage, drawback in each hypothesis or each assumption. And in this case here, or in general, we have to discuss how conservative. Conservative means when it's valid, when it's not valid. First of all, why this approximation? The approximation of this hypothesis came from the fact that if you look at the expression, original expression of the output equation, you remember the output equation is y or z equals h, not capitalized, of x. X is a vector. We can see here x1, x3, x2 is the vector of the variable which we are considering state and output. But they typically, the output doesn't have any dynamics. If I write z equals h of x, this means that this time here, this is equal this time here, but it's not the case. This means what I did here is not really an orthodox form. It's something which don't consider that the output equation is and a static equation. Here, the output equation is a dynamic equation. And this dynamics is reflected in the present of Ts. Look what happens, and then we discuss it there. If I assume this hypothesis, I will write instead of x1 of k, x1 of k minus 1, because I can consider equals, as if basically x1 of k is does not change over time, or change does not change at this stage. We have a few changes. This means I can cancel this. I have this equation, this expression here equals 0. This means Ts is not there anymore. This is very important, as I told you, that the dynamics is reflecting Ts. Do you remember in Gymnasium? Do you remember what I told you? Ts is there because we have a derivative. In Gymnasium, how we calculate the derivative? X1 minus x2 divided, if x1 and x2 are 2 points of a function, divided the distance in the domain. Do you remember? If you want, I can show you what I intend in Gymnasium. Excuse me. Do you remember? Something like that. What is the rate, the slope, roughly calculated? Excuse me. This was the changes between x2 and x1, or x1 and x2 over time. But of course, because we have dynamics, because we are changing, this means very important also to choose the interval which we have in between. In fact, we don't have Ts. In general, now we can have a static equation, which now we can see the left part at the same time of the right part. Now we will discuss the difference in between, but of course, this assumption here is valid when this difference is very small. This means no big change between x2 and x3. And when the difference between T2 and T1 is also very small. When both together, much better, but at least one of them which can guarantee that x2 and x1 don't change much. In our case means x1 of k and x1 of k minus 1, they don't change. Again, they don't change when the dynamics of x1 is quite slow. Quite slow means, this dynamics here is lower than, let me say, I don't know, something like that, because the difference in the same interval of time is larger. We can understand what I intend for dynamics. Dynamics in the common sense moves a lot. This curve here between T1 and T2 moves larger than this curve here. And moreover, if the interval is very small. Let me see if I forgot to say something, but if I forgot, I will come back. In any case, we have this orthodox form. Why orthodox, I say? Because, as I told you, the original form of the nonlinear systems that we have, the states we change dynamically, because the states reflect the energy, and we are interested to monitor the energy. And the output, it depends of states, of course. It's something which does not change dynamically because otherwise is not an output. What is the state? This means this form here is the standard one, but in order to obtain the standard one, I have to consider a possible approximation. Why that? Because originally the system, or better to say here, it doesn't matter, the equation one, excuse me, the equation one is a dynamical equation. It's not a static one. This means if I write in this form, which I am considering the output, this one, I force the system is something which is not natural. This means this expression here is not really natural. But we will see when, in any case, could be applied. Really, and then I would like to invite you to do, if you want, the more natural way to represent an output, it is one. But in any case, let me go ahead. The Jacobian, the derivative of x1 with respect to x2 of k minus 1 is x3 divided 2. The derivative of x1 of k minus 1 with respect to x3 of k minus 1 is x2 divided 2, no? Because once this is the variable, excuse me, is this is the state variable, this case, and the other case is this here, the state variable. We can see that this Jacobian does not depends of t. Let me see if I can add something, then I will open MATLAB and we will discuss a little bit more concretely what I am doing. I think I didn't forget to say anything, I hope. Let me think 1 second more. It could be a good project also to compare for different TS, for different configuration. Let me see if we can find nevertheless a concrete example. Probably we will see later with economics. Not extremely difficult to do this analysis. Could be nice. Could be nice. I don't know if I forgot to say something, but let me compare both variation in output. Let me open MATLAB. This week, as I told you, I will upload everything. Tomorrow I'm not in Lüneburg, but after tomorrow I have again lectures, a lecture tutorial, and then I have time to upload material. Okay, let me open MATLAB so we can discuss concretely this example. MATLAB, where is MATLAB? Where is? Oh, I don't find. Let me write MATLAB. Now, found it. Okay, just a second. I am uploading. I am, yeah, uploading. I am loading, better to say, MATLAB. Exactly now. Let me see if I find quickly. I am there. Let me share. Close this. Okay, advanced. Probably here. Exactly. Simulink second example state output non-linearity. Let me see. Sarah, is it difficult for you follow me in Kalman? Now better than before.
I think in the beginning it was grabbable for me. I think now with the advanced, it's a bit more. It's definitely harder, but I'm trying.
After that, if you want, we can discuss about your project. No problem.
Yeah, thanks.
And it's very important that you download the material, but I will upload a lot of things, then we can discuss a little bit again. Uh, but in your case, you want to do something in economics? I don't remember.
Yeah, no, it's more like informatics. In informatics, yeah. I will tell you about that later.
Yeah, we can
Okay.
discuss because I am here until 10 p.m. No
Oh,
problem.
okay.
No problem.
That's long.
Yeah, but I like if I can help, if I can help the students, really I can. I like.
Okay, thanks.
Because I don't have many students. Okay, look, now I share Simulink. Before Simulink, let me share Simulink. Where is? Yeah. Look, we can see exactly what I told you that I have to put a value of A, which Kalmat does not know exactly, doesn't know because must be estimated. This part here represents the dynamics, X1 dynamics. We can see X1 multiplied 2 with minus here, and here we have X2 multiply A with plus the input. I don't know if you remember. And here the nonlinearity. You remember this X2 squared. Multiply 2 with minus. Inside here we have X1. I think, exactly, X1. We have two equations, relatively easy. And here we have the Kalman filter. Realize this time, I already presented this embedded form. This embedded form. Okay, let me go inside the. Yeah, we have noise. Could be done, could be not done. To test typical is there. No, typical is there because we measure x1. You remember exactly what I told you as an output variable, but this variable is an output equation also. No? You remember z equal h, not capital I of x. I measured h. Excuse me, z. But z is x1 in our case, which is also an output equation or has an output equation. Let me come back in MATLAB workspace. Let me give, I don't remember an suitable TS. This is also an interesting problem, but let me, because do you remember, should be not so small, should be not so large. In this case, small should improve the second variation because do you remember I told you the second variation of Kalman filter, I come back on this. The second variation of Kalman filter is based on x1 of k equal x1 of k minus 1. But this is also valid or not so conservative if Ts is very small. And the first, let me show you this before running the simulation. This hypothesis is validated, or let me say is less conservative, if the dynamics, the variation of the function is small, and or if the interval is very small. This means Ts very small. With Ts very small in the practical application, this approach here should be more suitable with respect to this approach here. In fact, look, this approach here for Ts very small becomes very lazy because we don't have the variation. The Jacobian represent the variation. This means could be a problem, in particular if Ts is zero. A paradox, just to understand, if Ts tends to zero. Of course, this variation here becomes to be problematic because I need H, we can see here, not zero, in order to have a Kalman gain not zero. Just this could help to understand what I'm trying to test. This could be also an interesting project to test a little bit to analyze this kind of problem. Ts should be not so large, if you remember Shannon theory, but in general, very large Ts, we lose information on the dynamics, not just roughly speaking. Okay, excuse me. Let me give you a value. Let me come back to MATLAB. The value of A, which is Kalman does not know. I mean, the initial value of A is not 3. I don't remember which is, but we can look now together. Again, I am measuring x1 with noise. Let me say with noise. If it's not noise, better. But anyway, I have the possibility to manage the noise, no, with the matrix R. I delay this value here. I don't remember why now I am delayed here. Is probably I implemented at the end the last variation. Yeah. I show you what I intended, why I delayed this. Because it could be that I implemented this. You can see everything is delayed. We will see now. It could be, should be. This must be delayed, the input, because we are working with the forward Euler. No? I told you very quickly. Anyway, U is always in forward Euler of k minus 1. In backward or in different discretization, not necessarily k minus 1. Let me go here inside. We can see. No? Let me explain this, but this is always the same. Now we have to just to show you these two output Jacobian. Okay, Ts is the same, must be. If it's not the same, basically it should be better if I implement here as an argument of the function, so I cannot make mistakes. Ts must be for Simulink and MATLAB the same. x2 and x3 is 0, 0, okay. Yeah, do you remember this? I told you is empty. We need because in the other interpreted function, we put the initial value outside in Simulink. Here, we don't have this possibility. This means we have to put inside. for the state initial condition, but also for the a posteriori covariance matrix. We can see that everything is 2 times 2. We have two states. Q is again 2 times 2. Look, why so large? So large because the equation of x3 is a Gaussian equation. This means Kalman should have the possibility to move the values, to adapt, let me say, to adapt the value. This is the state, as I told you many times now. Yeah. Look, in fact, look, we delayed the measurement because I am applied here not this equation here, but this one. Now you understand why I delayed the x1, because x1 as x3 and x2 are time k minus 1. Exactly. This is the a priori estimated states, equation 8, you remember in the lecture. I copied from what I told you until now. I copied the equation. This means my states, the states in our case x2 and x3 at time k, equals the state, this is a vector, no? Column vector is here. At time k minus 1, ts, which multiply this vector here. I don't know if it's clear. This 0 here means exactly that x3 of k is equal x3 of k minus 1. Because this is a vector which consists of a column with the element x2 of k minus 1 and x3 of k minus 1. And just in the first component, I have to add this expression here, ts, which multiply minus 2 x2 of 2 squared plus x1 measured, because I measure x1. Let me to be more precise. x2 and x3 on the left part, I called estimated states as a vector, in a column vector. Here we have xa, which consists of x2 of k minus 1 and x3 of k minus 1 in a column vector. And you can see here plus 0. Here I have to add this element here in the vector. This means I am considering these two elements as in a column vector. And this element and 0 is in another column vector. Therefore, I add two column vectors, this and this one, in which we have a 0 here. The rest, I uncopy the second variation. Yeah, which is the difference just in h, no? The states are not change. This I copied from here. And you remember, this is the first variation of the out Jacobian. And this is the second variation of the out Jacobian. Now I apply this. No? Therefore, the state, the Jacobian of the state does not change. Therefore, I delayed the input. Ready. The rest is the classical Kalman filter. Of course, I have to be careful at the dimension. We have the dimension 2 in the states. And the innovation, what I am measuring minus the model, an output. Once this one, and the other one, this one. Now we have to test this because I delayed. Let me show you what happens. Run. Very important here is to estimate the parameter A. If the parameter A is well estimated, you can understand that everything is well estimated. Why that? Because as I told you, the Gaussian variables are the most critical ones. Because we introduce, let me say, a little bit artificially this model, or artificial is not so correct to say, but with a not structured equation. Gaussian states in a variable, of course, in a Gaussian form. This means with its variance, this means, okay, I think we are ready. Exactly where is A? This is x2. Yeah, A is here. Must be 3, no? I hope it's working. Seems to be that doesn't work. Let me see what happens. It's blocked simulations. Ah, it's running. It's running. By strange. Ah, it's blocked. Ah. Ah. 1 second again. Yeah, now, excuse me. I don't know why it's so slow. This I am estimated x2, and here estimated A. I share now. Yeah, we can see. You can believe me, it's not so bad. I think it should be better. But anyway, you can see that should be better. I mean, I have to tune a little bit. But believe me, if the more difficult parameter is good estimated, you can check at home that x2, the other states, will be estimated very well. Let me test the second, or the first in this case, in accordance with what I told you in the lecture variable. And then I don't want to present the last example with, we have another example, but we upload with the representation output with an example with a cosinus function. I will show you a little bit this economical system. It could be easy probably to understand. Let me now to go here inside. Let me, excuse me. Let me comment through this one, because in the first example, we don't have to delay, because we measure directly the output x1. This means comment through, and this means simulate that, not see this delay. If I go here inside, do you remember here? I have to comment this, and I have to apply this one. This was the don't care about this comment here. I don't know why it's there. And I have to consider this Jacobian here, which correspond to the equation which I activate now, and to comment this one. Do you remember I discussed a lot about TS, not TS? Should I show again the calculation in the sheet? I don't think so, no? Let me run now. Let me share A. Very important is A, believe me, x2, this is A. Let me see if this works. It could be that I need to tune. But we can see that it seems to be working. And a nice example of project could be, now we will try if you can formulate in this context, you have to analyze for smaller TS, as I told you, this example here, or this variation here, which I implemented before, should be more suitable, just thinking that if TS is very small, theoretically to zero cannot be zero, we don't have anymore a reaction of the Kalman filter, because Kk is going to zero. If Kk is going to zero, or the very small, the Kalman filter is not sensitive. Now we can understand why these complicated calculations, which we don't need exactly to understand, but intuitively it seems to be clear. Kk depends of this expression here, but if the expression here is very small, Kalman filter is not sensitive to get or to manage what happens for this variation here. Okay. The contrary, if the SC relative is large, this kind of Kalman filter seems to be more sensitive. This is a little bit what we have to compare. I think in a few, Sarah, do you have time for me? Are you sure? I show you a little bit another
Yes.
Kalman filter, and then, but just is scrolling down, because now I did this, I would like to show you. And then very quickly again, how we can do in economics, even though you are not interested in this, but it could be that if some student will look at the presentation, can contact me for economics, because here, you know that in our university, we are more oriented in economics, or at least in our faculty, at least, yes. Let me share. Let me. Where is very? Yeah. Why I don't see? Let me close again. Now here. Okay. I would like to skip everything. We have seen together this form of cascade, at least in one possible configuration. Yeah, we can see I insisting with this lecture, but would like really in 1 minute to show you this. I have an x of t and a phenomenon which is, let me say, regulated. X of t is a multiply sine of omega t, in which I measure x. This means this equation is the output equation. And I want to estimate amplitude and omega if this is possible. Now I will define a new variable, phi of t equals omega of t. If the equivariance of the sinusoid is constant, then you have something like that. Of course, this is an hypothesis. This is an hypothesis. But assuming that it's somehow valid. For the Kalman filter, we know that is not extremely important, because I can realize, I can manage this hypothesis, even though it's not totally satisfied, with this stochastic variable, no? Or that we can consider, in any case, in Kalman filter, the variables are stochastic. Starting from deterministic nature, we will realize in a stochastic form of the variables, because we put their variance somehow. It's the same here. I'm considering A as the constant. Now, I have 3 states, phi, omega, and 8. The derivative is extremely easy. because the derivative of phi is equal omega. The derivative of omega, excuse me, here I think I made mistakes. Let me see. Mm, uh, the first line, we have an 1 here. Excuse me for the error. I have to correct, because if you look here, the derivative of phi is equal omega. This means we have here 1 is here is 0 is here is 1. Let me see. In order to correct. Exactly. Excuse me for there. I have here 1 here, 0 here is 1 here. I will correct that we upload. And here we have a 0, 0, 0, because as I told you, omega is constant. I don't know, probably an error in LaTeX. We have here 0, 1, 0, and we have here 0, 0, 0, and we have here 0, 0, 0. Also here is a little bit strange, no? 0, 1, 0, correct? 0, 0, 0, 0, 0, 0. Okay, yeah. Which we can understand now exactly what is written here, because the first equation is correct. The derivative of the angular position is equal to the velocity omega. And these two are approximating. This means I will correct, excuse me, in the final version. 0, 1, 0, and everything is 0. Here also 1, 0, 1, 0, and everything is 0. But I think it seems to be correct here. Yeah, here is correct because, do you remember the discrete, the discrete form of the continuous matrix is the identity matrix plus T times, or the TS times, the continuous matrix. If you look here after the correction, 0, 1, 0, and everything 0, we have the identity matrix is 1, 1, 1, everywhere 0. And if I multiply this matrix by TS, I have just TS in this position here. But basically, what is written here is written that phi of k minus phi of k minus 1 divided Ts equals omega. Equal omega. I don't know if this is visible. Or phi of k equals phi of k minus 1 plus Ts multiply omega. The rest means omega k equals omega k minus 1. A of k equals omega k minus 1. Excuse me for this error here, but I will correct. Now, output Jacobian. Yeah, is the derivative of what? Of this expression here with respect to phi, omega, and a, the states. And we have this from Gymnasium. To be implemented is very easy. Please, excuse me for this error, but the final expression are correct. What we need to implement is this one. But I don't know, probably it's LaTeX, but I will correct. Last slide, if I find quickly, what we can do also with this with these tools. Bank. The bank, or is the bank? I show you just the model. Three minutes to discuss the model. Okay, I don't find, let me see where I can find. Okay, let me see. Mm, 1 minute more. Okay, probably here. It's not this one. Okay, I'm not able to find quickly. I think we can conclude, so we can speak with you about it's a shame.
What were you looking for right now?
I would like to show you in economical systems in which we can really apply the Kalman filter. But if you are not interested, it is not important now. But even though the idea is, if some students will look at the video, it could be that could be motivated to contact me because we have many students who is working. I think they have interest in economic. Uh, but I need time because I have so many slides, lecture. It's sometimes is. I think eventually I can communicate per Zoom, no? The last attempt. Probably I found something. Let me see. I found the simulation, but not the presentation. Pa, 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 pa. I think, let me see the last. No, it's not. I think I will upload in my study informing that we have also the possibility to apply um, the Kalman filter in the context of economics and in the context of pandemics. But here it's a shame I am not able to. Oh, probably I found something, even though it's not exactly what I would like. But let me show you. I need just 1 minute because I flesh out the model really. So we can look, and then we will discuss you and I about your project. It's not exactly the lecture because it's the presentation at a conference, but the topic is exactly what I want to show you. Yeah, we have here the definition of some elements in the economics. Probably the students know better than me. Assets, liability, equity, risk assets. Yeah, here we can see a possible scheme of control, but today, just in 1 minute, I would like to show you the model of the bank because in our case, in our course, we didn't consider the controller. We consider just an observer which can serve the controller. In which sense?
So sorry, I just for understanding, so the controller is also like it's not an instance that there's a person, it's really just someone who uses the data of the observer to correct
Exactly.
the.
Exactly.
Okay, so it's not a controller in the sense of like a business controller, right?
Yeah, it is.
Okay.
It
Oh,
is.
it is.
It is a little bit
Okay.
because the controller a little bit generate which decision we have to do in order to attain some goals.
Mm-hmm.
Basically, states the strategy, what I invest today, how much I invest today, how much I will invest tomorrow. Look at the title. Yeah, here's we have another paper, more interesting. Instead of sliding mode control, we have a model predictive control. It's not a strategy, but with help of Kalman filter. This means the controller, in order to predict, in this case, we don't have any real prediction. In order to predict what I can do tomorrow, he needs to estimate some variable which is not easy to get. I will show you in 1 second. This means, in this sense, is the strategy, they help us to, let me say, to determine the strategy to invest or to withdraw money in order to attain some goals. This was in a conference. Look at here, we have two states, liability and assets. The liability, Sarah, is the money which belong to you, but you don't have at home, you have in the bank. There's a big difference because if you have at home, it's not a state. But if you put in the bank, becomes immediately a state because the bank, with the interest, generates the dynamics. I mean, the money of today is not equal the money of yesterday, or not the money of tomorrow. Change over time. Now, probably the interests are not updated each day, but think about if this sample time is 3 months, I don't know, in the contract of the bank, because the system, we will see what change after the sample time. It's a shame. Okay, here a little bit too abstract. You have to discretize this model here, as we did today, in order to have a liability over time, but considered the contract which you have. If you update your liability, again, the liability is in a state because it's the money which belongs to you, but is in the bank. And if in the contract they say we update the interest within 3 months, the simple time is 3 months because we don't see variation inside. And if you invest or if you withdraw, we have to consider what we do within these 3 months. Here we are considering just 2 states, liability assets. And basically the assets is a more complex state because the liability you can measure, because you can count your money. You can have what you have each 3 months. The assets in the concept, in accord with what the student told me, a little bit more difficult to be quantized because it's the property, because it's complexes. And therefore, we measure the liability and we estimate the assets. And you can see the input is just in the liability because you can put money in the bank or you can withdraw in the bank. And this model here, which we took from the literature, they came, the model, the equations, they came from the literature. We try to control using the Kalman filter. But again, the last sentence, the idea is to apply the Kalman filter for the students, which we want to do on this system here. And then the control, this is a little bit more complicated because the control, more complicated. The topic does not belong to this course because it's control systems. Okay, let me stop here. Thank you for your attention. Now we can discuss together about your project. Thank you. Thank you.